want to tell you about is kind of geometric representations of affine W-algebras. And so, in some sense, the moral of the talk is that there's nothing affine about the answer. But
is anything geometric?
Certainly not. But so we're getting there. So let me sort of maybe start with some sort of introductory orienting comments. Okay, so if G is a simple Lie algebra, so associated to it is an affine Lie algebra. We recall is the central extension of the loop algebra we saw in the previous talk. And then there's a technical variant of the affine Lie algebra that shows up, which is the affine W algebra. And so this will be important later. So there's a version. So it's in some sense the affine W algebra associated to the principal nipotent element, or the principal nipotent conjugacy class in G. And so part of the interest in, say, this algebra is sort of W, say, it kind of arises in sort of quite a few contexts. Sort of a particular one is sort of in quantum geometric Langlands. So and so in particular, kind of there's some sense in which kind of its highest weight representations are sort of closely related to, e.g., representations of quantum groups. And so maybe the statement is just in the principal case, the representations of this W algebra, in some sense, it's useful if you're just trying to sort of pass between Langlands dual groups, and sort of similarly if you're trying to understand things like the Kazhdan listing equivalence between quantum groups and the Kazhdan listed category. And so in particular, the highest weight representations are something that you'd want to understand to be able to do these sorts of nice things. So these highest weight representations are, I think, fairly well understood by this point. So let me just remind you of a couple basic points of sort of how you think about them. So first, kind of going back to work of Fagan and Frankel, and then okay, I'm just going to start just writing first letters because I'll never finish the talk otherwise. So then Frankel, Katz, Wakimoto, and then so they kind of put down. Okay, well, I did not succeed in that. This is Arakawa. All right. Great. So say if we're trying to understand highest weight representations of this guy, there was some nice functor that went from the highest weight representations of the affine Lie algebra, and it's basically this was some sort of quotient functor. So this sense, this was T exact, and sort of it sent sort of standard slash Verma objects to sort of standard slash Verma, and it sent kind of simple objects to simple or 0. And
Should we put some restriction on the level?
no. And so, so the upshot of this was that if you knew the character formulas over here, which you did, you could just read off what the character formulas were here. So thanks to this nice functor. And sort of as a slight technical variation on that, kind of, so, you know, for people who know the definitions of W-algebras or this kind of thing, the one slight disadvantage of this functor is that, for example, the way you produce the W-algebra from the affine algebra is not through this functor. So it was through a slightly different functor, which is called the plus reduction. And sort of this functor is kind of, so it has the advantage that it sends sort of the Kac-Moody vertex algebra to W, but sort of, and relatedly for people, you know, for things like fusion, like you can't use this functor, you have to use this one, but the downside is it's slightly more complicated to sort of understand where sort of individual objects go. And relatedly, sort of things like t-exactness, like, certainly fail. And so, nonetheless, why don't I just switch this? So nonetheless, there was kind of some nice work of also Frankel, Katz, Wakimoto, which kind of sort of nonetheless sort of you can show that when you take the reduction of certain simple highest weight modules. So for people who know these types of words, it's things like admissible representations. These went to 0 or shifts of simples. And sort of the simples you get from these ones are sort of, you know, the analogs of say minimal models for the Virasoro algebra. And kind of there's a version of that for all of these W algebras. And so, so I checked that thing was true. So anyways, the upshot is that for principal things, you want to understand the highest weight representation theory. And you know, this is like the main chunk, and then you know the other things people expected you also know are true. And then just a last comment is kind of related to both of these. Yeah. Sort of, you also have sort of a geometric picture of their representations. And so there's a version of this that applies to every single block. For simplicity, let me just tell you the answer in the case of one block. And you know, if you want, I can tell you afterwards what the general thing looks like. So, for example, if you take a regular block, the regular block at say an integral level, so then the point is that when you take these highest weight representations, you can just think of these as D modules on
What is 0?
just regular block. Yeah.
And all categories are derived.
Yeah, everything's derived. Yeah. So, well, you can write down T exact things, but then you have to be careful about the level. So let me just write down derived things and not care about the level. Okay. Let me just quickly give you some notation to say the answer. So it's going to be on some space cooked up from G. So let's write G for the simply connected group. The algebra is G. Let's write O for Taylor series, F for Laurent series, and so in particular we have GF, which is the loop group, which kind of, it looks like matrices whose entries are Laurent series. Okay, so and let's write G of O for the arc group. So it's the subgroup of sort of all your entries are just Taylor series. There's no poles. And then just as one last piece of notation, so because there's no poles, it makes sense to set T equal to 0. And so if you pick a Borel, you can make this Iwahori subgroup. So you're supposed to think of this as some affine version of the Borel, and relatedly, so if you take this quotient, this is called the affine flag variety. And so if you want to get W modules from it, what you do is, well, okay, then inside of here, you have the pro-unipotent radical of Iwahori. And you take things equivariant for that against sort of, this is some character, I naught, which in some sense is kind of, it's cooked up from the same character or principal nilpotent element that gave you W. So the details of this equivalence, which is due to myself and Sam Raskin, don't matter at all for us. The only thing I want to say is that how do you look at this category?
Important is that
Yes. Yes. Thank you. Yeah. Hold back from generic character. Okay. So you can ignore, like, if you don't know or care what a D module is, you don't really have to know or care for this talk. Just the thing I just want to say about this is, what's another way to write this category? So what it looks like is it's some category on just the finite dimensional flag manifold, and then you just tensor it up to make it have anything to do with affine things. Okay? And okay, so sort of we're using the fact that, you know, if you have functions or D modules on some double coset space, they'll act like convolution on sort of related double coset spaces. Again, the only important thing for this is that sort of at the level of Grothendieck groups, you get the following picture. So this thing looks like the finite vowel group. This thing looks like the affine vowel group. And this looks like the sign character of the finite vowel group. And so, you know, for people who are familiar with how character formulas for these types of categories are written, they're written in terms of combinatorics of Hecke algebras or Weil groups. And basically, it's this type of picture underlies the combinatorics of the character formulas for the W-algebra. So roughly, if you just had this, you would just have, you wouldn't have this sort of extra tensor product term. And sort of passing from Kac-Moody to W-algebra, it just turns on this tensor product. It turns on this kind of like anti-spherical quotient. Okay, so
We should understand that when the level is negative, the equivalence above is too exact.
absolutely. That's okay. Okay, so that's kind of the picture. And so what I want to tell you about today is sort of how does this picture extend to other W-algebras? So let me just say a couple words about that. So again, so what about other nilpotent conjugacy classes? And so let me just sort of say that, so for each of these, it has its own W-algebra attached to it. And sort of, so again, sort of, for applications, so one wants a good understanding of highest weight representations of this animal. And let me just mention one of these things because it's relevant to a lot of other stuff in this conference. So particularly, so Davide Gaiotto has, in collaborations with some other people, he's introduced a lot of really spectacular conjectures, kind of for certain sub-principal, for non-principal nilpotent elements. And so there's been lots of work on this stuff. Let me just mention a few names. So there's, the acronyms, okay. Witzig, Linshaw, and then kind of Braverman, Finkelberg, Ginsburg, Travkin, Yang. Sorry, I forgot some names. Okay, so the point is just that
Usually it's some names or all names.
yeah, let me just put like A through Z in probably. The point is just that like there's a lot of nice conjectures that if you understood the highest weight representations of this guy as well as you did in the principal case in particular, you could solve a lot of these conjectures pretty straightforwardly. So
Can I ask a question about some other letters?
please.
It's about letters H and W. What exactly highest weight representations do you consider?
Oh, so like
Is it like the full category O?
yes.
It's like equivalent with respect to the maximal torus in the centralizer plus, loop rotation.
So yeah, I mean
Some people not only mention names, they also give definitions.
yeah, so let me say the following thing. So quick definition, and again, the details don't matter for us. It's take the things you know for the finite W-algebra. So that's the Jou algebra of this guy. There's a version of parabolic induction to produce modules. Take the full subcategory of W modules generated by those guys.
By which guys? Guys from category O?
Yeah. Sorry. Yeah. So this is kind of so it's generated by parabolic inductions
One dimensional, no? From which representation?
of sort of the category O for the finite W algebra. So
Particularly if I were to take E equal to 0 We just get the usual affine category O.
Yes, thank you. So, example, if E is equal to 0, is usual affine category. Affine. Okay. So, and let me just tell you, sort of the basic thing which happens is just we just change this and we change this, but otherwise it all kind of looks the same. I think that's kind of the work in progress. Okay, so that's what I want to tell you about today, and so to do that, let me So let me recall / reformulate some facts for finite W-algebras. And namely, I want to say things in a way that will kind of make this business of just, oh, you just have to change this and change this, kind of, I want to state that in hopefully a pretty transparent manner. So to do that, I need to sort of recall some setup. So to do this also, sort of, let me just recall kind of, so for people who've never really thought a lot about nilpotent orbits, so here's kind of a basic picture of nilpotent orbits. So the basic idea is that they have a kind of Harishchandra, and sorry, this word is like super overloaded. So there's some whole story in representation theory where you think about like, there's things you can build from smaller levies in kind of by some sort of induction, and then there's things which are just genuinely just from your Lie algebra and you can't get them from a levy. And so those are kind of the cuspidal things in some sense. So they have kind of some cusp form.
The problem is that there are exactly two ways to do it.
Yes, and I'm about to tell you which one I mean. Yeah. And so, so namely, so if I take E in my Lie algebra, sort of, I can ask for L a minimal. So forget about the minimal for a second. I can ask, is it actually sitting inside the Lie algebra of a levy? And then if that's the case, then I can take that levy and say, like, well, is it inside a levy and the levy, and keep on going. So I might as well just go to a minimal levy subalgebra containing it. Okay, and so if L is strictly inside of G, the rough thing you'd want to be able to say is that you can control things for G and E sitting inside it via L and E sitting inside that via induction. And I'm saying this kind of vaguely because I'll make it more precise in our context in a second. But okay, so that's kind of saying like the things that came from smaller subalgebras, you can just hope that if you understand the smaller subalgebra story well enough, you'll understand your story too. But then, if there's a second case where if L equals G, so E is called distinguished. And so these are kind of the analogs of cuspidal representations. And so let me just give you a couple examples to get a feel for this. So inside SLN, sort of the only distinguished, oh, sorry, actually, so example 0 is the principal E is always distinguished. Example 1 for SLN, that's the only distinguished element. And so let me tell you a stupid way to restate that. So if I make the generating series for the number of principles in SLN times q to the n, that's just 1 over 1 minus q. Okay. Questions about that? Okay. But so.
What was that word about next to highest weight generated by what?
Parabolic inductions.
Parabolic induction.
Yeah. So, just we'll get to like the relevant. We'll get to that in a second. You don't have to worry too much about it. Okay. So then the statement is that in the other classical groups, there are way more distinguished elements. So example 2, sort of in symplectic groups. So if you write down the same series, so you're trying to count principal conjugacy classes in SP2N, you get the following thing. So, okay, so there's the principal every time.
You mean distinguished?
Thank you. Yeah. Sorry. Okay, so there's the principal in every single one. That's example 0. But then now, so the sub principal, so meaning that there's the unique conjugacy class, which is sort of just below the biggest orbit. That's the sub principal conjugacy class. So this is distinguished in SP sort of 2n for 2n greater than or equal to 6. And then you keep on going. So there's 1 minus q to the 5th, 1 minus q to the 7th. You keep on running forever. Okay, so you get a lot of distinguished nilpotent orbits pretty quickly. So here's a sub-example. So the number of distinguished orbits in SP 114 is 7,197. Okay, so you get a lot of these things. And then for the orthogonal groups, there's a similar formula. Let me just tell you, so it's kind of, it looks almost the same, but it goes up and down. So you kind of go up and down forever. Okay, so anyways, the upshot is that there really are lots of distinguished conjugacy classes, not just the principal one, but you can, the exceptional groups, there's some explicit classification. In the classical groups, you can just break them down. You can count them, there's no problem. Okay, so in some sense, let's believe in this philosophy that we can probably control everything if we understand kind of the cuspidal case, or this kind of this distinguished nilpotent element case. So what do we mean by the category O sort of for the finite W algebra when E is distinguished? And sort of the answer is we just mean a finite dimensional representation. And so again, so let's just do an example. So sort of if E is equal to 0, and as we're talking about just the usual category O, when is E distinguished? So that means that G is just a torus. And then we just know that sort of category O for a torus, that is just rep of the torus, right? Algebraic representations. Or maybe you can go off the lattice too, but you know, the point is it's just finite dimensional representations. Say it's just finite dimensional representations. So we need to understand what the analogous classification, or enough of it, looks like for not just 0, but everyone else. So let me give you a nice way to say this. That it'll take a second to explain how it relates back to this, but it'll make all these kind of Weyl group combinatorics kind of transparent. So let's do the following thing. Okay, so E was our distinguished element. We can put it into an SL2 triple, and this gives us some particular H grading on our Lie algebra. This is kind of its H grading. So a nice fact is that for distinguished things, this grading is all even. So for people who are experts in this kind of stuff, that makes technical stuff easier. Let's not worry so much about it. So let's write the corresponding subgroups. So I'm only going to write 2 of them. So this thing exponentiates to P, some parabolic subgroup of G. And sort of this thing exponentiates the kind of U minus some sort of like the unipotent radical of an opposite. And E, the thing we started with, it gives us a, so E determines a character sheaf on U minus. So more explicitly, think about, say, taking the trace of E times your thing. That defines a map from this Lie algebra G less than 0 to C. You can exponentiate it to get a map from U minus to GA. And that's kind of a homomorphism. And then you can just pull back the exponential character sheaf to get this thing. So. Okay, so again, details don't matter. The point is there's some nice character that comes from. Okay, so.
Why do you need distinguished? You don't need distinguished.
So far, I don't need it yet. I'm not using. Yeah, that's a good question. Thanks. Okay.
Well, if it's not distinguished, it will not be even. If it's
Yes.
not even, then E doesn't quite work as a character.
Yes, there's a game with the Lagrangian and the one, yeah, whatever. Yeah, but so far, for any even thing, this is the exact same thing. Okay. So, yeah. So here's now the key point. So here's here's an important proposition due to Bezirkovnikov, Braverman, and Mirkovich. And they say that, okay, so we want to somehow do something with these 2 groups that we've introduced. So let's just sort of play them on opposite sides of G. Okay, so let's look at this category. It claims that this thing, say, if you take the Schrieg fiber at the identity element. Okay, so that gives a map to vect, the category vector spaces. And this is an isomorphism. So, in other words, i.e., in some sense, the only object on the left-hand side, only object means, you know, is a unique simple object, for example. The only object on the left-hand side is just e to the psi on the big cell u minus p inside of G. Okay. So again, so let's just think about an analogy. So analogous statement would be that if you take functions on G of fq, mod p of fq, mod u minus fq, and you can write down some analogous character, this thing is one-dimensional. Okay. Okay, and so here you have some action of some Hecke algebra. So I'm going to stop writing the FQs. So here you have some character of that Hecke algebra. So similarly here you get some character of this Hecke category. So let's think about what this gives us. So this gives us the following thing, which is, so again, what this means in sort of down-to-earth terms is that if you take functions on G of fq mod P of fq, that contains a unique vector which transforms like that. So another way to say that is, so basically, there's a unique irreducible module, which I'm going to call Steinberg. It's going to depend on P, but I'm going to suppress that from the notation. So there's a unique irreducible representation of this finite group, which can fit inside these two things. So if I take functions on G mod P, and I take functions on G mod U minus psi. Okay. And concretely, what is this thing? So Steinberg P, it just equals I take functions on G mod U minus what am I trying to say? Thanks. Great. I take functions on G mod P, tensored over functions on G mod P with functions on G mod P mod U minus psi, and that just sits inside functions on G mod U minus psi. So in other words, we're saying that like there's only one thing in here that has some sort of degenerate Whittaker model, and let's just take that guy. So then, the way we've written it, we don't have to think very hard about how we write down the analogous category of sheaves. So namely, then we can set D modules on G, which are Steinberg equivariant. That's just going to be the analogous tensor product. So I take D modules on G mod P, I tensor them over D modules on G mod P with D modules on G mod P, which is going to have this big cell thing. Okay. Okay, so the idea is that this is some sort of categorical version of Steinberg P. Okay. And so now, in particular, this just sits inside D modules on G, which have this equivariance property. Okay. So as a consequence, you can talk about Lie algebra representations sort of. So if you take Lie algebra representations which are U minus psi equivariant, that's exactly all representations of this finite W algebra. That's kind of the Scriabin. Scriabin. Okay, great. And so we have this thing inside it, and the claim is that this turns out to exactly be the finite dimensional representation. And so we'll get there in a second. But so let me just tell you. So
Is this statement true as stated?
oh, okay. For integral central characters, thank you.
Does it have all possible extensions?
Yes. So generalized integral central character. We can talk about it after. It's completely formal that this is going to be closed under extensions, the way I've defined it. Okay. Anyway, so let's just do an example.
So how would this
Yeah.
compare with the fact
Yes.
that there is a functor from category O which lands in some equivariant objects
Yes.
instead of just all modules?
Mhm. Yeah,
Does it
forget
have
that close under extensions. This. We start with the parabolic category. Why don't we talk afterwards? I'll also explain more of what you're asking about in a second. So suppose we're trying to calculate what just these representations are. So we fix sort of the trivial central character. Okay. So so this looks like, so if I just take this, that's just D modules on G mod B. Thanks to the localization theorem. And we're taking sort of this Steinberg part, these Whittaker invariant.
mod P?
No. Taking this. I'm just saying, let's just look at what's the contribution with trivial central character. I'm saying just the algebra representations of trivial central character are the same as D modules and G mod B. And then just take whatever equivariance we care about along for the right.
But what is G mod U minus psi Steinberg?
That's the question.
It's okay. Here's a form. Okay, I avoided a formal definition because.
Because you avoid definitions, yes.
Yes. Okay. So here's a formal. Okay. Whenever you have a category acted on by D modules on G, this thing is defined to just be, it's the equivariant functors from the category I just defined to C. And just because this sits inside D modules on G, this sits inside the original category. Okay, whatever. I mean, just the point is, and it's all I'm saying is that just again for free, like this sitting inside this, you can now talk about analogous chunks inside Lie algebra representations. Okay. Okay, so we have this is the same as this, and so this is just D modules which have this equivariance property, which kind of so we also just have still this convolution action of G mod B mod B. And so recall, I promised from you at the beginning that all of this theory will look the same as the principal case, but we just need to change some representation of just some little finite Weyl group. And this is exactly the change. Okay? So this thing, let me recall to you, this is basically just the finite Weyl group. And the claim is that this sort of categorifies an irrep row of the finite Weyl group. And let me make that slightly more precise right now. So here's a proposition. Well, okay, first let me first give you an informal explanation, and then I'll give you a formal statement in a second. So this category kind of categorifies the homomorphisms from Steinberg P to functions on G mod B. Okay? And now the point was that, so Steinberg P had a unique of the scalars map into functions on G mod P. That sits inside functions on G mod B. And so let me recall for you, so this thing, what it looks like is it looks like a direct sum over irreps of the finite Weyl group of, so let me say pi. So for each of those representations, you can just sort of think of it as a multiplicity space or as the corresponding module for the Hecke algebra times some, let me call it capital pi. This is not a good choice. That's the corresponding rep of G of FQ. So I'm just saying, this is just restating the fact that the endomorphisms of this representation are the Weyl group, or rather it's a group algebra. So the point is that, so this thing is so irreducible, how many times can it show up in here? It's just one of these things, therefore the multiplicity it comes with is just the dual Weyl group representation. Okay? So therefore, so rho is equal to r pi for some unique pi, which implies that this space is just sorry, what? I'm sorry, Steinberg. So this point is that this Hom space just is necessarily rho. Okay. And so now let me tell you how you say all of that in the categorical context.
Wait.
Yeah.
Rho is a representation of the
Finite Weyl group.
irreducible.
Irreducible. Yeah.
Which I would guess is just a special representation corresponding to the given special nilpotent orbit.
Yeah, we're about to get it from Springer theory, which I think is your question. Yeah. Let's see what it is in terms of Springer theory. Okay. Okay. So here's the precise proposition. Say if I take, again, and just ignore words that you don't care about. So if you take the Hausfeld homology of this category, this is canonically isomorphic to rho as vector spaces.
Could you please translate this specifically to me to Springer theory?
Yeah, I'll say it in terms of spring theory right now. So what's the idea? And there's actually something kind of, it's going to be interesting to me, and we'll see how you feel about it, Ivan. So what's the point? The point is that, okay, so okay, interlude. So okay, analogous thing for the finite groups would be the dimension of this space of Homs, which is equal to the dimension of rho. Okay, and the point is that, so this would be the Homs from G mod U minus psi Steinberg to G mod B. And this is as G of FQ representations. Okay? And the point is that you can get this by, that's some inner product of their characters. Okay? Okay, so the point is that you can calculate dimensions of Homs by sort of pairing characters, right? Okay, and then the point is that in exactly the same way, this thing, it's going to be sort of, okay, there's details here that you should not care about. So again, sort of characters, they live, characters of representations live in functions on G mod G. And kind of the pairing is some sort of integral over this finite set, right? So you can just do the exact same thing, which you can take the character sheaf of this Steinberg category and sort of you pair it with the character sheaf of functions of G mod B. And then, so then a nice other observation is that, so the claim is that the character sheaf of just this Steinberg thing, so that's a summand inside the character sheaf of just sort of D modules on G mod P corresponding to this, the character of, okay, so what's the right way to say it? So this is some sort of Rosendiek-Springer sheaf. So sort of the way people normally say this is like, you have some sort of Springer action of this algebra on this sheaf. So if this was just B, this would be the normal Springer action of the Weil group on the Springer sheaf. So this action actually just comes from the fact that it's a categorical trace. So namely, this is just the Hochschild, well, this maps to the Hochschild homology of just D modules on G mod P mod P. And this for free acts on the character sheaf. So all I'm trying to say is that, like, the Springer action of Weil groups on all these sort of Springer sheaves and all its technical variants, they're actually just kind of, they're built into this categorical trace formalism, or rather you can get them from this categorical trace formalism, and relatedly, it captures very well the intuition that the action of the Weil group on the Springer sheaf is somewhat coming from the fact that the Weil group was the endomorphisms of the corresponding representation of G of FQ. So it's really kind of just, you can use this stuff to get all these sorts of things we're familiar with. Okay, anyway, so this is some summand corresponding to the character of this that we met before. Details do not matter. And so then now, this pairing the right-hand side becomes from sort of it essentially becomes a Hom between two sum ends of the Grothendieck. Let me just say it just becomes rho. Sort of. I'm using the fact that the character of functions on G mod B that has this decomposition into, again, irreps of the Weil group, now some IC sheaf tensored with. So the point is that what I'm saying is that this Steinberg thing corresponds to just one of these sum ends without any multiplicity. So all I'm just is again like the fact that we're going to get some Springer representation type thing is just wired into. We just kind of can deduce it algorithmically from the setup. Okay. Anyways, so let me sort of now just kind of get back to what we actually care about. So here's a maybe concrete theorem. So let me break it into two parts. So both of these are due to Ivan. So it says the following thing. So take the reduction functor from G mod P to G mod U minus psi. So note is that sort of the essential image generates this by definition. So we might as well just put it like this. But this is just the Lie algebra homology. Okay, so here's some claims. So one is this is T exact. Two, it sends sort of standard objects to certain let me just call them standard objects on the right-hand side. So just think of it as just some very explicit objects in this category. And
Objects whose dimension, you know.
whose dimension we know.
That's how explicit they are.
Yes, dimension we know. And we also know their composition series or whatever. Yeah. But anyways, and then 3 is sort of it sends simple objects to something. Well, I'm going to write it as semi-simple or 0. Now, of course, I could have just written semi-simple, but anyways, like this almost looks like the type of statement we had before. So let me sort of say that this much, as I've written it, is actually, this is not hard to prove. And it's it's almost automatic from that theorem of Bezrukovnikov, Braverman, Mirkovich I said before.
Well, when I was proving that it wasn't so automatic.
Yes, no, but the next thing I'm about to say is not at all automatic, and it's a serious theorem of U and Ostrich. I just wanted to sort of distinguish between what seems like, where's the hard work and where's kind of the, okay. Okay, this is really, okay. So the statement is that, in fact, let me just set this up for later. Let me just write this as a lowercase psi minus. Okay, so then the claim is that actually sort of simples, in fact, go to sort of 0 or an equivariantly simple object. And what do I mean by equivariantly? mean, sort of everywhere here, there's some.
Well, actually, it's a theorem in that paper that you try to quote as something trivial. It's not only for strings.
Thanks. Great. Okay. Okay, great. So, again, I'm not saying that paper's trivial. I don't think it's trivial. I'm just saying this part I can prove, so it's trivial. This part is hard. It's interesting. Okay, so, or equivariantly simple object. And so, basically, there's some centralizer, there's some component group, some centralizer floating around, and when you put that in, you really get simple things. Okay, so, let me now tell you, having said all this, what's supposed to be happening for happening. Okay, so let me just affine case. Okay, so we can start with the algebra G. Take a nilpotent element. And sort of pick a, what do you call this, Q? Pick a parabolic and a levy such that E is distinguished in L. Okay. So then let me recall for you. So from what we had before, we had some irreducible representation, rho, of the Weil group of L. Okay. Oh, and sorry, let me give you one other fact. So this thing is, so 0 or not is, so maybe non-zero if and only if the Gelfand-Kirillov dimension of the representation is maximal. Meaning for anything in this parabolic category O, there's some biggest dimension it could possibly be. If it hits that, you live, otherwise you die. That's the analog of people who know the principal case well. It's like this business of like, is your weight anti-dominant? Okay, so then here's kind of the, I'm going to call this theorem in progress. Okay, so there's a, so there's a similar reduction functor that go, oh, sorry, and so, okay, so let's write, so we had P inside of L from what we had before. So this was the parabolic associated to E. And then sort of, let's take sort of, we take its pre-image inside of Q, make this larger parabolic. Okay, and okay, so then, and then let's finally write IP bar for the corresponding parahoric in G. So then we can take these modules, we can consider there's a minus reduction functor, it's W modules, and this has the following properties. So it's T exact, 2 kind of standard, co-standard, goes to kind of standard, co-standard, meaning kind of Verma type objects. And 3, sort of simple goes to kind of equivariantly simple or 0. Again, in terms of just the Gelfand-Kirillov dimension of just the corresponding representation of L. So the point is, you can take this, and you can read off a bunch of character formulas And let me just sort of
Caleb,
Last
dimension
minute.
for the representation of a finite guy.
yes, just the levy
It's
of the distinguished. Yeah, exactly. Okay, and then some two last comments. We're kind of so one there was a very nice paper, Katsuruan Wakimoto, which in particular introduced these W-algebras for non-principal nilpotents. So they have some conjecture that, again, there's some sort of plus reduction, and it should send admissible things to sort of a shift of an irreducible or zero, and sort of conditional on this, as long as you just put some word like equivariantly irreducible, it's true. So follow. And then the last thing I just wanted to say is that, again, the picture of the category is we get D modules on the loop group, which are now kind of, let me just horribly abuse notation. So again, you just kind of induce something from what we had before. And then, again, the upshot is that the way you picture this is, it's what this looks like is, it's the affine vowel group tensored over the vowel group of this levy now with rho, that irreducible representation of that. Okay, that's all I wanted to say. Thanks for your attention.